This is Lesson 12 in our Calculus 2 series, Integrals with Trigonometric Substitution. In this lesson, we're learning another method of substitution that will help us compute our integrals. So let's take a look at why we need another method of substitution. If we take a look at an integral like this, 1 over x squared radical 16 minus x squared, we might think to try a u substitution with u equals 16 minus x squared. And then with that, du is negative 2x dx. So we would need a negative 2x up in the numerator here. So let's see if we can manipulate this to work. We put in a negative 2x in the numerator and then also in the denominator to compensate for that. Now keep in mind that because we have an x in here, it needs to stay inside the integral. The negative 2 can come out of the denominator as a negative 1/2, but this x needs to stay inside the integral. And simplifying here, we have x to the third in the denominator, and so we need to figure out what x to the third would be in terms of u. So if u is equal to 16 minus x squared, then x squared is equal to 16 minus u, and so x to the third power would be x squared to the 3/2 power, which would be 16 minus u to the 3/2 power. So that's in our denominator, which means that we would really have 16 minus u to the negative 3/2 power there. And this would be u to the negative 1/2 and du. And we would have our negative 1/2 on the outside. And this is the best that we can do with our regular u substitution, and we can't solve from here. So we do see the need for another type of substitution to help us compute this integral. Now, because of the trig identities, sine square theta plus cosine square theta is equal to 1, and from that we get tan square theta plus 1 is equal to secant square theta. Because of these trig identities, we can make the following substitutions. For the expression radical a squared minus x squared, we want to make the substitution x equals a sine theta. For radical a squared plus x squared, x equals a tan theta. And for radical x squared minus a squared, x equals a secant theta. Now let's take a look at why that's useful. Notice that in radical a squared minus x squared, where we substitute x is equal to a sine theta, then we have a squared minus this x squared becomes a squared sine square theta. So we can factor in a squared here. And then this 1 minus sine square theta gets replaced by a cosine square theta. Now we have a radical cosine square theta, and that will simplify to cosine theta. So we have an a cosine theta. So this substitution allows us to get out of this radical, and that's extremely helpful when we're integrating. Now let me be a little bit more careful and talk about the intervals on theta for which these are valid. Notice here for radical a squared minus x squared, this expression only exists when a squared minus x squared is greater than or equal to 0. That says x must be greater than or equal to negative a and less or equal to positive a. And so it does make sense to talk about x being a sine theta. We know the sine theta values vary from negative 1 to positive 1. But keep in mind that when we're making this substitution, we want to make this a unique substitution so that we only want theta values that are going to cover that interval only once. So we're restricting to theta values from negative pi over 2 to pi over 2. Now remember, this is the same interval that we restricted the domain for sine theta to so that we can talk about an inverse function for sine. So it's the same idea here. We want to make this substitution, but we want it to be a unique substitution, so we want to restrict theta to be in this interval. Now for radical a squared plus x squared, because we're adding here, this sum is always going to be greater than or equal to 0. X can take on any value, but again, we want those x values only to be taken on once for each theta. So we want to restrict our substitution here for theta values between negative pi over 2 and pi over 2. Again, the same interval that we restrict to when we're looking for an inverse function for tan theta. And similarly for radical x squared minus a squared using the x equals a secant theta substitution. And then when we make this simplification here, we can in fact simplify radical cosine square to cosine theta because we know that cosine theta is going to be greater than or equal to 0 on this interval. This is the interval for which this substitution is valid. And we know that on that interval, cosine of theta is greater than or equal to 0, so this simplifies nicely. And that's going to happen with all of these substitutions. You're always going to be able to cancel the radical and the square of the trig function. And that's why these substitutions are so useful. So let's take a look at that same first example, the same integral we were looking at earlier. Here we see a radical 16 minus x squared. So this is our a squared minus x squared under the radical, and so we want to let x be 4 sine theta. Right here, radical a squared minus x squared, x should be a sine theta. Here we have a squared is 16, so a is equal to 4. We're always going to choose the positive square root of that number, so a is equal to 4, and x is equal to 4 sine theta. Now we have to be careful here. If x is equal to 4 sine theta, what's the relationship between dx and d theta? If x is equal to 4 sine theta, then dx is equal to 4 cosine theta d theta. And so now we have this relationship between dx and d theta, and so we want to replace this dx by 4 cosine theta d theta. So that our integral will now look like this. X squared gets replaced by 4 sine theta quantity square. Similarly here. And then dx gets replaced with 4 cosine theta d theta. And so now we want to do a bit of simplification. And our 4 sine theta quantity squared becomes 16 sine square theta. Same thing in here. We factor our 16 under the radical. We replace the 1 minus sine square theta by cosine square theta. And then we can simplify here to 4 cosine theta. Again, because cosine theta is greater than or equal to 0 on this interval. Now we can cancel the 4 cosine theta in numerator and denominator, and we're left with 1 over 16 sine square theta d theta. So we can pull out the 1/16, and this is cosecant square theta d theta. Now we know that the integral of secant square theta is tan theta. The integral of cosecant square theta is going to be something about cotan theta. Is it positive? Is it negative? I always forget, so I take my derivatives to check. Here's my derivative of cotan theta using the quotient rule, and that's negative cosecant square theta. So that tells me that the integral of cosecant square theta is going to be negative cotan theta plus a constant. And let's not forget the 1/16 from the outside. So now we just need to simplify and answer back in terms of x. Now we can write this back in terms of x by solving for theta. If we have x equals 4 sine theta, then x over 4 is equal to sine theta, and theta is equal to arc sine of x over 4. So we can write it this way. But we definitely need to simplify this. So we're going to have to set up a triangle. So you could either write it from here or from here, letting theta be the angle in your triangle. We know that x over 4 is equal to sine theta, so opposite over hypotenuse is x over 4. That allows us to compute the remaining side. And now what is it that we're looking for? We're looking for cotangent of theta. So we need adjacent over opposite. Adjacent over opposite. And so that's going to get plugged in for cotan of theta, or for cotan of arc sine of x over 4, either way. And so our solution looks like this. Let's take a look at another. Now in the last problem we noticed that we couldn't use regular u substitution, we could only use trig substitution. But in this problem we would be able to solve it with either kind of substitution. So let's take a look at both methods. So here we have x to the third radical x squared minus 1 in our integral. So by noticing the composition, we might try u equals x squared minus 1, and then du equals 2x dx. So we realize that we have a u under the radical, and we need one factor from this x to the third. We need one of those x copies to go with dx so that we can make our du. So I'm going to pull off one of those copies of x and I'm going to bring it over here. I'm going to multiply in by the 2 that we need, and so multiply by the 1/2 on the outside. And now we're here. And so here we have a radical u, here we have du, and here we have x squared, but we know that x squared is going to be u plus 1. So here's a u plus 1, radical u, du, with a 1/2 on the outside. And so now we can take this u to the 1/2, or this radical u, and multiply it through, and then it becomes a basic integral. And simplifying, we're here. Now we can get the same solution using trig substitution. We see the x squared minus 1, so we're thinking x should be 1 secant theta, because this is of the form radical x squared minus a squared, and in this case a is equal to 1. So if x is equal to secant theta, then dx is equal to secant theta tan theta d theta. And let's make our substitution. So x is equal to secant theta, so this is a secant to the 3rd theta. Here we have a secant square theta minus 1 under the radical, and dx is secant theta tan theta d theta. And this secant square theta minus 1 simplifies to tan square theta under the radical, and that simplifies to a tan theta. And simplifying, we get integral of secant to the 4th theta tan square theta d theta. And this is an integral of the type that we saw in lesson 11. And so here we're going to want to make u equal to tan theta, because we need a secant square theta then for du, and then the secant square that remains can be written in terms of tan square. So this secant to the 4th theta, we're going to make secant square theta times secant square theta. This secant square gets replaced by tan square theta plus 1. And so now we have a u square plus 1 times a u square times du. And so multiplying through and integrating, we're here. In terms of theta, that looks like tan theta to the 5th over 5 plus tan theta to the 3rd over 3 plus a constant. But remember that we need to write this in terms of x to complete our solution. So we know that x is equal to secant theta, so that's x over 1 is secant theta, and that's hypotenuse over adjacent. So here's our triangle. Hypotenuse over adjacent is x over 1. And then our remaining side is radical x squared minus 1. And so tan of theta, opposite over adjacent, is radical x squared minus 1. And so that gets substituted in for tan theta here and here, and that's our solution. And it's the same answer we got using a regular u substitution. Let's take a look at another. Integral of 1 over radical 9 plus x squared. I'd like you to take a few minutes and work on this problem on your own, using a trig substitution. Here we see the radical a squared plus x squared, so we make the substitution x equals 3 tan theta. And then from there we get dx is equal to 3 secant square theta d theta. So we make our substitution here. We factor the 9, and this 1 plus tan square theta gets replaced by a secant square theta. So now we have in our numerator 3 secant square theta d theta, and in our denominator a 3 secant theta. So simplifying, we're left with integral of secant theta. And we learned in the last lesson that is ln of absolute secant theta plus tan theta plus a constant. Now we do need to answer in terms of x's again, so we need to simplify this and write it in terms of x. So we know that x is equal to 3 tan theta, so x over 3 is equal to tan theta, and so this is going to just be then x over 3. And we need the triangle to get a representation for secant theta. So tan theta is x over 3, that's opposite over adjacent, so the hypotenuse is then radical 9 plus x squared. And then secant theta, which is hypotenuse over adjacent, is going to be radical 9 plus x squared over 3. And so that'll go in here. And so our solution looks like this. And if you want to combine and make one fraction, we can write it like that. We could also separate this into two logs, log of the numerator minus log of the denominator. Either of those is fine. Now notice if we had a definite integral, if we have bounds on this integral, how does that change things? Well, notice that by making the substitution, we went from integral of 1 over radical 9 plus x squared dx to integral of secant theta d theta. And the substitution was x equals 3 tan theta. So when we make that substitution, we're going to want to change our bounds to be bounds on theta. If x is equal to 3 tan theta and x is equal to 0, that would say that theta must also be equal to 0. When x is equal to 4, we have 4 is equal to 3 tan theta, so 4/3 is equal to tan theta, and theta must be arctan of 4/3. And so that would be the upper bound here. And then we can integrate and plug in these bounds and compute. So we'd have to take secant of arctan of 4/3. So we would need the triangle for that. We let this be theta, and that tells us that tan of theta is equal to 4/3. So tan of theta opposite over adjacent is 4/3. And so secant then, which is going to be hypotenuse over adjacent, is then 5/3. And so that goes here. And tan of theta we said is 4/3. That goes here. Also plugging in 0, we have secant of 0 is 1, tan of 0 is 0. And this simplifies to ln 3. So it's not necessary to go back to x. We can just change our bounds and move forward with theta. But if you did want to go back to x, you would of course get the same answer. Now let's take a look at another example. Here we have integral of 1 over x squared plus 4x plus 7. And this doesn't look like it fits into any of the forms that we know how to handle. But we can complete the square and change how this looks. So remember, completing the square means that we're going to take this quadratic and we're going to write it as x plus or minus a number squared and then plus or minus a constant. So how can we do that? Now in this case we have a leading coefficient of 1 here, which makes the problem much easier. In the next example we won't have that and we'll have to deal with that as well. But for now we have a leading coefficient of 1, so it's a bit simpler, and we take a look here at the positive 4 and we divide that by 2, and that gives us a plus 2. So we're going to have x plus 2 here, quantity squared. Now in order to take what we have here and wrap it in this form, write it as x plus 2 quantity squared, we need an extra plus 4 here, because x squared plus 4x plus 4 is equal to x plus 2 quantity squared. So we're going to add in a 4 and then subtract a 4 as well. So these terms get wrapped as x plus 2 quantity squared. Here's the minus 4 we had to put in, and here's the plus 7 that we started with. And these combine to a plus 3, and so we can write x squared plus 4x plus 7 as x plus 2 squared plus 3. And we've completed the square. So here we have 1 over x plus 2 quantity squared plus 3. Now if we let u be x plus 2, du is then dx, and this is 1 over u squared plus 3 du, which you might have memorized to be 1 over radical 3 arctan of u over radical 3 plus c, and then we can go back to x's from there. But if you haven't memorized that formula, let's go through the details. We want to make this 3 a 1, so we need to factor a 3 out of our denominator. So we're going to pull out a 1/3, and that leaves a u squared over 3 plus 1 in our denominator. And this u squared over 3 gets written as u over radical 3 quantity squared. And so now we have a u substitution, or we're in variable u already, so I'll call it a w substitution with an arctan integral. So w equals u over radical 3, dw equals 1 over radical 3 du. So we need to put in a 1 over radical 3 here, which means we need to multiply by a radical 3 on the outside. And then we have an arctan integral. And subbing back in, we get radical 3 over 3, arctan of x plus 2 over radical 3 plus c, plus a constant. So now we have radical 3 over 3 arctan w plus a constant. Remember that w is u over radical 3, and u is equal to x plus 2, so we're here. This is our final solution. But if you didn't think of this arctan formula or of factoring out, you could also use trig substitution to solve this integral. Now, after completing the square, we made the substitution u equals x plus 2, and we're here. Integral of 1 over u squared plus 3 du. So here we could recognize this as like an x squared plus a squared, and so we would let u, in this case, u equal radical 3 tan theta. Remember that a squared is equal to 3 here, so a is equal to radical 3. So u is equal to radical 3 tan theta. And then du would be radical 3 secant square theta d theta. So squaring u for our denominator would give us 3 tan square theta, then plus 3. And our du is radical 3 secant square theta d theta. And so we could factor a 3 out of our denominator and bring that out with the radical 3 on top. And we have 1 over tan square theta plus 1 times secant square theta d theta. We know tan square theta plus 1 is secant square theta. So these will cancel, and we're integrating just d theta. And that integrates to theta. So we have radical 3 over 3 times theta plus a constant. Now what's theta? We know that u is equal to radical 3 tan theta. So that says u over radical 3 is tan theta. And we know u is equal to x plus 2. And so we have x plus 2 over radical 3 is equal to tan theta. And so theta is arctan of x plus 2 over radical 3. And so we plug that in here, and that's our solution, the same solution we had before. Let's take a look at one more problem that needs completing the square. Integral of x over radical 6x minus x squared minus 5. And notice if we tried regular u substitution here, we would have u equals 6x minus x squared minus 5, and so du would be 6 minus 2x dx. And we don't have this 6 here. We don't have that extra constant hanging around here, so that's not going to work. So we are going to use trig substitution here, but we're going to need to complete the square. And so let me just give you a little heads up on that. Here, with completing the square, I want you to rewrite this in order, right, having the highest power first, so negative x squared plus 6x minus 5. I want you to factor out the negative and complete the square inside the parentheses. Okay, so factor out a negative from the entire expression, and then complete the square as we did before, all inside the parentheses. So please pause the video and complete your square, and then compute your integral. So completing the square inside the parentheses, we realize if this is x squared minus 6x, we need a plus 9, so that this can be x minus 3 quantity squared. Again, we're taking what we have here, our negative 6, and we're dividing by 2. That gives us a negative 3. So we have x minus 3 quantity squared, so that's going to be x squared minus 6x, and we need a plus 9. So we put in a plus 9 and subtract the 9 as well, and then carry down the plus 5 that we had. So we regroup and we get x squared minus 6x plus 9 gets wrapped up as x minus 3 quantity squared. Combining the negative 9 and plus 5, we get a negative 4. And so we're here. And now we can distribute that factor of negative 1 on the outside of the parentheses. And so we have negative x minus 3 quantity squared plus 4. Or if we want to reverse the subtraction, we have 4 minus x minus 3 quantity squared. And so that's what completing the square is going to look like for this problem. And so our original integral can be written as x over radical 4 minus x minus 3 quantity squared. And now we recognize this denominator is of the form radical a square minus x square. Well, we don't exactly have an x square, we have an x minus 3 square. So if you want, you can let x minus 3 equal u and make a u substitution there. Or you could just move forward with x minus 3. Here we would let x equal a sine theta. So here we let x minus 3 equal 2 sine theta. X minus 3 is equal to 2 sine theta. And then dx would be 2 cosine theta d theta. And in our numerator we're going to have an x, and solving for x here would give us x is equal to 2 sine theta plus 3. And so our integral would look like this. Here's our x minus 3 quantity squared, so that's going to be 4 sine square theta. That goes here. Here's our x, which is equal to 2 sine theta plus 3. That goes here. And here's dx, which is equal to 2 cosine theta d theta, and that's here. Or if you're more comfortable using a u substitution first, you could let u equal x minus 3, and then with that, du would be equal to dx. And then we would make the substitution u is equal to 2 sine theta, u is equal to 2 sine theta, and then du would be 2 cosine theta d theta, and we'd end up in the same place. So we factor our 4 under the radical in the denominator, and the 1 minus sine square theta gets replaced by a cosine square theta, and then radical cosine square theta is equal to cosine theta. Radical 4 is equal to 2. And so we have a 2 cosine theta canceling with a 2 cosine theta, and we're left integrating 2 sine theta plus 3. So we have negative 2 cosine theta plus 3 theta plus a constant. And now going back to x's, we know that u, or x minus 3, is equal to 2 sine theta. So that sine theta is x minus 3 over 2. And theta is equal to arcsine of x minus 3 over 2. So that's going to go in for theta here. And we also need to compute cosine theta from a triangle. So x minus 3 over 2 is equal to sine theta. So opposite is x minus 3 over hypotenuse of 2 allows us to compute the adjacent side as radical 4 minus x minus 3 quantity squared. And so cosine theta is going to be adjacent over hypotenuse, so that's here. And this will go in for cosine theta, which means our 2's cancel, this 2 and the denominator 2 cancel, and so we're here. And this is written in terms of the completed square, but if you'd like to go back to the original by multiplying this out and simplifying, that's here. And that's our solution. So again, trig substitution is another substitution method that's going to be useful when we have radical a square minus x square, or radical a square plus x square, or radical x square minus a square. And this is because of the trig identities and the simplifications we can make from that. Now, before we end this lesson, I just want to point something out that might make it easier to remember the trig substitutions. Notice that with each trig substitution above, a triangle was made and the substituted expression was one side of the triangle. This can help you remember the substitution. So for example, in the first problem that we looked at, we had radical 16 minus x squared. Now when we look at the radical 16 minus x squared and we think about the sides of a right triangle and the Pythagorean theorem, we realize that this must be one leg of a right triangle whose hypotenuse is 4 and with the other leg having side length x. So that triangle would look like this, and using this angle as theta would give us the substitution that we had above. We have sine theta equals x over 4, and so x is equal to 4 sine theta. So here I'm saying start by looking at the expression for which you need a substitution and see where that would fit on a right triangle. This would have to be a leg of a right triangle with hypotenuse 4 and other leg equal to x. Now if you had set up your triangle like this, using this angle as theta, you would have cosine of theta equals x over 4, and so x is equal to 4 cosine theta. That would also be a valid trig substitution. Just from there, dx is equal to negative 4 sine theta d theta, and continue from there. And with this problem that we saw above, integral of 1 over radical 9 plus x squared, we look at the radical 9 plus x squared and recognize that with the Pythagorean theorem for right triangles, this would be the hypotenuse of a right triangle, so that the legs of the triangle would have length 3 and x. And so you can start by looking at this expression, putting that as a hypotenuse and setting up your legs 3 and x and going from there. And here we have tan theta equals x over 3 as the simplest expression to begin with, and that's the trig substitution that we're going to make. X is equal to 3 tan theta. So just keep this idea in mind when you're using trig substitutions. And with this, we'll conclude our lesson on trig substitution.